Who, me or?
Alan. Everyone else.
Yeah, okay. Okay, well, welcome to the March talk taking place in early April. And welcome Sandy Etchells, who's going to be presenting on explosives in the mining industry and how to make them safe. I've known Sandy for a good 17, 18 years when I first met her at the University of Natal, Durban in South Africa. And from there, via email mainly, I've heard about her progress through various companies, De Beers, the South African Explosive Group, and other places of interest. So I'll let her take over now and she can share her screen and give us a talk about explosives.
Excellent. Thank you, Mark. Just let me get the screen sharing part right. Okay, can everyone see my screen?
Can I suggest everybody but Sandy just goes on to mute and onto no camera?
I can see it though.
Excellent. Okay, so as Mark asked, if everyone can go on mute and take your cameras off, and then maybe if you have questions, just pop them in the chat. I can't see anything in the team screen anymore. I can only see the screen that I'm sharing. So thank you for the introduction, Mark, and thank you for having me tonight. It's a really good, I really appreciate the invitation, and it's a subject that I'm very passionate about. So yeah, I think a lot of rock engineering people focus on, you know, the support aspects of rock. So when you excavate a slope or an underground tunnel, you're looking to support the rock mass and not damage it. So there's another section of rock engineering which I really got passionate about, and that's understanding how the rock breaks, and obviously the application of explosives to do this rock breakage. So I specialized a little bit in the explosives engineering side, and then combine that with the rock engineering. So, okay, wait. There's this, sorry, just a technical glitch here. Can you see the second slide? I'm assuming yes. Okay, so these are just some references that are stuck in here. They're all available online. Otherwise, you can just drop me an email and I can send them across. So what I'm going to talk about tonight is a little bit of an introduction to explosives itself, then looking at rock breakage mechanisms, understanding the blast modeling process, and then applications in blast modeling. See, there are people waiting in the lobby. Is anyone else able to admit people, or is it only me?
I think I could admit people because their signs pop up, Sandy, so I'll have a go.
Okay, great. So I can focus on presenting.
Yeah.
Thank you. So, okay, what is an explosive? In short, it's a chemical substance that's able to detonate. And in the application of mining, it's used to break rock as part of the larger mining process, eventually to liberate the minerals. How does it actually break the rock? Sorry, I've got another screen blocking my view here. Too many screens at the moment. So how does it actually break the rock? So what happens, you release energy in the form of very hot and high pressure gases. So these gases, it generates heave, which is also known as rock movement. And the resulting muck pile is what is mined out. In addition to this, it also generates a shock wave. So by definition, a shock wave travels faster than the speed of sound. And what happens is you get a pulverizing or a crush zone, which forms within the immediate vicinity of the blast hole. So this can vary according to the explosives properties and also the rock engineering properties of the material. But typically it would be 2 to 3 hole diameters. When I talk about hole diameters, I'm talking about the blast hole that you've loaded the explosives into. So Different types of explosives have different properties, and the key is to adapt your blast design to then achieve the results you want to get, as well as to provide adequate protection to either the final high wall or the final tunnel excavation. So on a broader scale, sorry, I think there's some echoing. Maybe if everyone can turn their sound off. On a broader scale, the primary explosives are very high energy explosives used in very small quantities. So I've got two examples here. We would normally use a detonator and a booster, a pentolite booster. So these are used to initiate the secondary explosives, which are usually used in larger quantities and have lower energy. So in terms of explosive properties, some also have higher shock energy, which contributes more towards the fragmentation of the rock or the breaking up of the rock according to the different rock properties. And then other explosives would have more gas or heave energy, which is useful to move the rock and generate fracture mechanisms. So ideally, you would want to find a balance between the two, because then these two different properties work in combination with each other to give you like the optimal results that you want. So I've shown you the example of the primary explosive here. This is an example of a secondary explosive, bulk emulsion. And here is ammonium nitrate porous pearl, which is blended in with the bulk emulsion. This is an example of packaged or PEX explosives, or different kinds of cartridges. So the contents of the cartridges can either be an emulsion type of explosive, or can be a water gel, or a blend of the different companies have different proprietary blends. So the emulsion itself gets sensitivity, allowing it to detonate from little gas bubbles inside it, or microballoons, which are basically tiny particles on which hotspots can form, which then supports the process of detonation through the whole explosives column. So what is detonation? So it's physically and chemically quite a complex subject to describe, so I'm not going to go into too much detail tonight. But essentially, if this is your column of explosives, you would have a chemical reaction front. It's an exothermic reaction, which produces a shock wave, which propagates through the explosives column. So that propagation is very rapid, and then has a chemical reaction zone behind it, which is where the production of the different high temperature, high pressure gases are formed. So the nature of this reaction zone is dependent on the type of explosive. So for example, military explosives would have like a very ideal behavior. So this line mathematically and physically would be defined by the equations, would be quite straight. And in other words, the nature of the detonation wave would remain constant across the whole diameter, whereas commercial explosives are different in that you have more non-ideal behavior. So the chemistry basically causes that reaction to slow down, or the characteristics of it to change towards the periphery of your whole diameter. So essentially, your products that you give out is energy in the form of the shock wave, heat, and then your gaseous reaction products. So it's these gaseous products that is a very high pressure that then applies a force against the rock mass. And that force is what then, according to the different rock properties, causes the rock to break, to put it quite simply. So the different blasting energies that you have, we spoke about shock energy and heave energy earlier, and those in combination would then first break the rock, and secondly, it would also move the rock. A third type of energy which is produced is basically lost energy, and that comes in the form of ground vibrations, air blast, and fly rock. So fly rock is actually fragments of rock, usually as a result of poor charging or poor blast design, and it basically is thrown out of the blast hole as don't know how to explain it, but it's literally ejected out of the blast hole as a flying rock, which would then have a trajectory and land in some unintended place. So often large amounts of gas energy can also travel through poorly orientated joint systems within the rock mass. And this stray energy can also cause damage to the final excavation highwall. So in a strip mine, for example, coal mining, where you use drag lines, a large amount of heave would be required to move the rock for the drag line to be able to reach it. So you can see how the different mining applications lead you to change the type of explosive you use and also to optimize the blast design to give you these different results. The design, it can accommodate this without too much intervention on the high walls, because in a coal mine, the high walls are only needed to stand for 3 to 6 months, and they're usually not the main access route to the remaining ore body. In the case of a large open pit mine, where final limit blasting techniques are required to protect the high walls and also to protect the ramp systems, which is your main access. So there we would use techniques such as pre-split blasting, and these can take a significant amount of time and cost because they're quite a specialized kind of blasting technique. But it also allows the pit slope to be optimized, and large amounts of energy that you generate during the blasting process can be controlled. So an example on the very extreme end would be in civil engineering, where you would perhaps cut a rock slope against a road, and it's obviously on a different level to mining because you've got to have a lot more controls in place. So this is just a diagram in terms of the different types of blasting energy and you know, what happens to it. So you've obviously got the airwaves, the shock waves traveling through the air. You've got the shock waves traveling through the surface of the ground. Then you've got the shock waves that are generated more deeper, and these move differently according to the different rock properties, and can also be reflected or refracted depending on changes in density, changes in saturation levels, like for example, where you've got water tables or perched water tables, and geological structures. Items that can be impacted would be like your infrastructure on the surface, for example, this house, or you can have a building, and also underground mining workings, for example, tunnels. So in terms of the energy of explosives, how do we actually measure it? So it's measured through a concept called velocity of detonation. So you can model this using different detonation codes, and that takes into account the theoretical physics models versus the nature of the commercial explosives, because as I explained earlier, the characteristics would be slightly different in terms of the shape of that shock front. You would then go and measure this in the field to assess the performance of the product. So you can actually physically do a measurement to measure that velocity through the explosives column. So referring to this graph here, basically it's just showing the different types of velocities that you would expect. So this is in meters per second. So an average emulsion that we would use in mining would normally be like a 30% emulsion with 70% of ammonium nitrate porous pearl. Sorry, that's the other way around. 30% ANPP, the ammonium nitrate porous pearl, and 70% emulsion. So they would sit around here, and it would have an average VOD of maybe, this is theoretical, 6 to 6,500 meters per second. In reality, due to in-field effects, you would probably only get maybe 5,500 meters per second, and that is what you would go and measure. So what enhances or gives you a good velocity of detonation? So it's usually determined by the confinement properties. So this is where rock mechanics plays a really big role, because you know your rock mass properties are usually a given factor. You can't engineer them. the geology is what it is. So your intact rock properties that would impact your velocity of detonation would be your uniaxial compressive strength, your tensile strength, Young's modulus, Poisson's ratio, also the saturation conditions of the rock mass, joints, faults, foliations, shear zones, groundwater, anything that changes the way those shock waves are able to move through the rock mass and changes the nature of the tensile cracks that are formed. So another very important item that controls the performance of the explosives is the stemming material. So for some of us on the call, this might be a new word. Basically, it's a crushed gravel, and it has a specific diameter, which is optimal according to the blast hole diameter. And then you design it to a certain length. And that's basically meant to, so as your emulsion detonates, it produces all of these high pressure gases. So the stemming is designed to contain those gases inside the blast hole for as long as possible, so that the pressure can be exerted against the rock mass to optimize the breakage, as opposed to just ejecting out of the top of the blast hole. So I'm not going to go into a lot of detail on the rock breakage mechanisms because it's quite a complex subject. But just to simplify it, you would basically have your blast hole here, and that's where your detonation reaction would take place with your explosives. This would immediately be surrounded by a crush zone. So everything in this crush zone is pulverized. It just doesn't exist anymore. And that's due to that high pressure shock wave. That shock wave deteriorates exponentially with distance. So just outside of that shock zone, you would get a zone where you've got radial cracks forming. And as this moves through the rock mass, these radial cracks, then generate more radial cracks, and eventually they will reach maybe a discontinuity where they'll either be reflected. Sometimes it'll reach a change in density where they're refracted. But basically that shock wave continues until it reaches the edge of your rock mass. And at that point, you'll get spalling occurring. Basically, that's essentially your free face on your, we call it the free face on your blast face. So then a reflection takes place. So the wave is compressive in nature as it gets towards the face, and then it's reflected back in tension. So you've got tensile stresses and compressive stresses acting, and then basically the cracks extend and extend and eventually pulverize the rock into optimal size fragments. So how do we get this process right so we get the right results? So it's not just a matter of just throwing in a bunch of explosives and hoping for the biggest bang. You actually want to optimize this process. You've got costs involved. You want to control the wasted energy. You want to get the right size fragments designed specific for your equipment. You want the right amount of movement on your muck pile, also specific for your equipment to load it. So we try and model the process as best as we can. So your rock engineering department would sit with the rock mass model. Then you would have your explosive engineers using their explosives model. Your blast design would be done looking at your geometry, and you'd have an initiation sequence. The initiation sequence is describing the sequence in which your detonators are initiated. Because remember, on your blast pattern, you might have 500 blast holes, and they're all initiated at a different time in order to get the best interaction between the holes for the best rock breakage. And then you can also have numerical blasting models, which are a much more advanced, it's a much more advanced model, and you could do blast design optimizations on this, considering all the different inputs that go into it. So for example, different inputs you would have different rock mass conditions. So you might have hard, massive rock, for example, basalts. You might have very heavily jointed rocks, or you might also have soft, massive rocks. This is in the copper belt from it's from the DRC, the Democratic Republic of Congo. So it's all very weathered, very soft, weathered material at the top. So you've got a lot of different extremes, and you have to be able to optimize your blast design according to all these different rock materials. So yeah, most of you will be familiar with your rock mass modeling and your different parameters that go into your joint model. And obviously the orientation of these joints is quite important in terms of the direction in which you're blasting. So this is just 2 videos. They're actually both from the UK. These 2 videos was a quarry mine, both using electronic detonators. So in the first example, you've got a very jointed rock mass, and in the second example, the rock mass is more massive. So you can get very good results from both types of rock masses. A lot of the time, when you get poor blasting results, people like to blame the geology when really the geology isn't an excuse to get poor blasting results. In terms of the explosives model, so the inputs that you would look at or you would have to consider would be the density of the explosives, the velocity of detonation, the detonation pressure and the pressure volume relationships. So these are all in relation to the gases that are produced, and then the overall energy that results from it. So that was the input number 2. Input number 3, you would look at your blast modeling process. So now this is when you start to look at the interaction of multiple blast holes and how, because remember earlier I showed you the rock breakage process around just a single blast hole, but now you've also got to consider how these holes interact with each other. So there needs to be an optimal spacing and burden, which is the distance between rows. Here you can see the sub-drill design, which is the section of extra hole that you drill in order to get a nice floor, a nice level floor that you mine from. This is your explosives charge length in red. And earlier on, I spoke about confinement. So that's where your stemming material, the length of your stemming material, to hold in the explosives gases for the right amount of time. Right at the beginning, I showed you the different types of explosives, where you have the primary explosive and the secondary explosive. So the primary explosive would be your primer, that would be your detonator and booster, and typically that is positioned at the bottom of the blast hole. So that's where you initiate from, and then the explosives column would detonate upwards in that direction. This is just for an example using a single primer, like your bench would be maybe 12 to 15 meters high. But in some different mining scenarios, you can get holes as deep as 20 to 30 meters, and you can have multiple primers throughout the length of the blast hole. Another important point is the position of the blast holes, and then obviously the face profile. Earlier, I showed you how the blasting waves, once they get to the free face, which is this portion, the surface here, the blasting wave is then reflected backwards in a tensile wave, and also spalling happens at the face. So this would change the behavior of the rock movement. So that's another important part of the blast design that you have to control. And then lastly, the actual hole initiation sequence and the delay timing that you use between the holes. So by manipulating the delay timing, you can control the way in which the material is thrown or the way it moves forward, the heave. So I'm just going to flick through the slide. It's just an example of a blast design. And then this would be an example of how you look at that whole initiation sequence. So you can actually, so these are contours, basically holes that are fired at the same time. So it's timing contours. So that can show you the overall movement of the rock mass. And then your numerical blasting model. So you would take all your model inputs, your rock mass model, your explosives model, and your blast geometry, and you would input it all into your numerical model. So yeah, that's just a very quick overview of the blast modeling process. So to kind of understand, besides obviously the fragmentation of the rock, or that's the way the rock breaks, important applications would be on your slope design optimization. So from a geotechnical engineering point of view, this is probably one of the primary functions. We want to look at the performance of the catchment berms and obviously elimination of fatalities due to rockfall on these catchment berms. So yeah, I've got two different examples. So, you know, the type of rock, the type of geology that you're working with can have a very big influence on these outcomes, as well as the drill and blast quality control processes on how the explosives are applied. So here your controls are really good, obviously, and you've also got quite good geology to work with. And in this case, it was solid rock, it was basalt, and there wasn't a lot of jointing. So we could have got good results, but just the drill and blast process, you know, there was not a lot of good controls on it. So unfortunately, you can see here how the catchment berms have been compromised and how they basically, either they have been blasted away, so they're not there to begin with, or they have been filled with material from previous blasts and not cleaned properly. So the stability of the slope high wall is quite important to realize return on investment in the open pit mine scenario, and then for that risk to be quantified and managed. Because an optimized slope angle then implies that, you know, the mining process is optimized and the slope design is in order as well. So you have to be able to implement a design that is effective in this. And poor final limit blasting techniques, when I talk about final limit blasting, I'm talking about the techniques used to excavate a very smooth high wall between these two examples. So if these techniques are poor, you can get really unsafe high walls and have excessive risks. So by understanding the blast damage mechanisms, you can just model this better. Once you can model something, you can start to manage it. And once you can manage it, you can obviously then start to optimize it. So first you would optimize it at bench scale, and ultimately you'll be able to optimize the overall pit slope. So if we have to look a bit deeper into these damage mechanisms, you've got rock type. So different final limit blasting techniques work more effectively in certain rock types than others. So in a very hard competent rock, a pre-split works very well because it basically creates a crack along the wall, the perfect tensile crack, almost like cutting a cake using decoupled explosive techniques. This decoupling means the explosives are not in contact with the rock directly, and they're basically suspended on a type of sausage string, often using packaged explosives, and it allows the rock to break under tensile forces with no compressive waves. So this air gap that is then created by the split prevents, so first you create this air gap in the rock, and then when you come along and do your production blast later, it prevents the shock waves from that production blast traveling past that air gap into the slope high walls. That's just like it's like a horizontal buffer. So it doesn't work very well in soft rock because the forces that create the split, it doesn't really propagate easily to get a tensile crack as effectively. So here one can use a different type of technique. It's kind of like a buffer blasting technique. So it's a very soft blast against the edge of the wall, and then you can come along and load it nice and smoothly with an excavator. So the spacing of the pre-split holes is quite important. If we go back to the pre-split that we were talking about in the hard competent rock, because yeah, if you get the spacing wrong, then the tensile crack doesn't really propagate properly. So sometimes you would you would have to do a few design iterations until you can get like the best result. So yeah, often, I don't know if you've seen in road cuttings, you would here I've got a picture, you would get these half barrels on the wall. So here you can also see them. So you would be able to assess the wall by using a half cast factor. So what percentage of the wall has got these barrels that are, you know, regularly spaced along the wall. You can see the drilling has been perfectly straight, and there hasn't been you know, massive movement along joints due to the blasting forces, as in this example over here. So yeah, this picture down here shows you some of the design iterations that were done using the numerical model by changing the spacing design. And yeah, this shot over here, basically your explosives weren't properly decoupled. So there was a lot of contact with the explosives on the solid rock mass, which caused that pulverizing crush zone to extend where it shouldn't have existed at all. There's also a concept called a trim blast, which is, you know, not your main production blast. It's a smaller blast next to your high wall where you decrease the quantity of the explosives. And yeah, you basically have like a 2/3 whole charge. So the design of those trim blasts is quite important because often the pre-split can be perfect, but then the trim blast comes along and smashes everything out of the high wall. So major joint systems can be unfavorably orientated with respect to the blasting direction. And what happens in this case is gases. So earlier we spoke about confinement. So the confinement is provided by the surrounding rock mass and the stemming on top. So now if you've got a major open joint, the blasting gases can preferentially go through that open joint. And then that can basically, if that's alongside you, if it has access to the hull wall through that joint, it can allow those blasting gases to go into the hull wall and cause a lot of damage. Okay, so there's a few other factors as well, but I'll just move on to the next slide. Oh, here's the last point, burden relief. This is what I wanted to speak about. So burden relief is basically talking about, you know, as your blast holes are propagated from the front of the blast, the rock is broken and then moves forward. So you've got a new free face forming after that material is broken. So essentially where the explosives doesn't see it as solid material anymore. So that relief, or that that formation of that free face, you know, moves back along your blast. But if your design is not optimal, that free face can get choked up, and then that also causes energy to be pushed back into the hull walls, as opposed to being used favorably to break the rock mass and move the material forward. So basically, it's very good control over where the energy goes from your explosives. So this is just an example to show how blasting damage to the high walls and what we did to try and optimize this. So we found on this scenario, there was at least 10 meters of backbreak. So you can, I don't know if it's very clear in the photograph, but this is not a natural rock joint. It was actually induced from the blasting. And that kind of damage went 10 meters back into the rock mass. So you can just imagine how you've compromised your rock slope. So in this case, what we did is these iterations on the design, where we were able to optimize the spacing and get a better formation of the tensile crack and improve the overall conditions. So another application of the blast modeling is where we've been able to look at the effect of the jointing and the blast orientation. So you can literally change the direction in which you're blasting to get better results on your high walls. Particle velocities of the rock mass is quite an important design factor. And we're able to model the borehole pressure. So that's the pressure of the gases inside your borehole. Then the face velocity. So that's the velocity at which the rock moves out from the free face. And then also model the velocity of detonation. So that was an atrocious blast using very old technology. They were using shock tube instead of the electronic detonators that is more favorable. And yeah, there was just rubbish all over the place. So what we did is we looked at how we can change that. So the energy is not just wasted the way it was, but is actually used more optimally to get a smoother profile. I don't know if this will play or not. Maybe not. Okay, so with the numerical model, we were able to take this design scenario and to then run different scenarios of how to change the design until we were able to start to simulate something that gave better results. So it's quite an iterative process because the models for blasting, it's not like doing the simple rock mass models that you use for slope designs. Yeah, it's quite complex and it's quite hard to get that dynamic shock to be considered in the numerical model. So several attempts in the industry have been made to build these models, but there hasn't been a single successful model that's taken beyond just the R&D scope. So yeah, that's quite a big area of research. Yeah, so some of the research that's gone into the subject is, how to link a lot of the theory, because blasting theory is still not as advanced as some of the rock mechanics theory. And yeah, how to simplify the whole blasting process. So, take a single blast hole, model it theoretically, try and simulate that in real life, compare the results. And of course, everything is great in a solid rock mass, but as soon as you add joints and natural discontinuities, it just becomes really, really messy. So this is another application that I've been working on recently. So in this scenario, we've got an open pit mine, which is coming towards the end of its life. And there's an underground mine that's being developed underneath it. So earlier I spoke about one of the third forms of energy, vibration energy. So you can just imagine the blasting vibrations and how they have to be controlled to prevent damage to this underground development. So yes, it's quite a detailed piece of work. Each surface blast is being modeled to try and predict the blast vibrations from the model, and then to see what blast vibrations we can accept from a geotechnical point of view on the underground development, and at what point there will be damage to the tunnels, and what designs we need to do in the open pit blast design to either reduce those vibrations or to keep them constant and then basically rehabilitate the underground development. So it's quite a balancing act between the two. So this third photograph here is just a seismograph where we basically have set up stations in the underground tunnel development where we're monitoring the blast vibrations that are received from the open pit surface blasting. So yeah, that's all from me today. I don't know if there are any questions. I don't know if the meeting is still here. And everyone's
Yeah, we're still here. Yeah, we're still here.
Or if I put you all to sleep.
I didn't hear any snoring, so I think you're okay. Ollie, do you want to take over and ask questions?
Oh, sorry. Yeah, there's no questions in the chat yet, so if anybody has any, you can just unmute yourself and.
Hi there, Sandy. Thank you very much for that. I was just going to, it's not specifically about that, but it was, how do you find going through airport security? Because they're always checking for things, and I just wondered how somebody like yourself who's dealing with it regularly.
I've learned how to wash my shoes properly and change my pants before I fly. And I made the mistake once of coming directly off a blast pattern, and I must have been contaminated on my pants and my shoes and my hands and probably everywhere. So yeah, I never made that mistake again.
Yeah.
And now I always have a change of clothes with me.
Yeah.
So as long as the contamination is inside your suitcase and checked in luggage, then it's fine.
Yeah.
He's got his hand up. Do you want to go ahead?
Yes, Alan.
Right, I've got a question for you. It's a long time since I've been involved in this, but how do you nowadays determine joint roughness from your point of view? I've been involved on and off for probably 40 years plus on that.
Yeah, so joint roughness was something I did long ago when I used to actually map faces. So yeah, when I did either the core logging or the face mapping, I would use a scanline technique, and I would actually use the Laplace scale and measure it by feeling it with my hands. But yeah, that was quite a long time ago since I've actually done that. Now other people do it and give me the data.
Right, okay.
Is it?
So do you do it in relation to what I'd call spacing of joints and the roughness in between the primary joints or something like that? How do you quantify it? Is it just an amplitude and that's it? Amplitude and wavelength of the roughness?
Yeah, it would depend if you're using the Q system or the Laplace RMR system. And I mean, there's an actual diagram which describes the joint roughness, and you would give it a rating based on that diagram. So yeah, obviously that's a standardized mapping technique.
Yeah, so this is something like Nick Barton would have done, but 40 years plus ago.
Yeah, exactly.
Yeah. Okay, thanks.
Beth, do you want to go ahead?
Yeah, I just had a question regarding, do you ever, when planning out the design pattern for the explosives, do you ever find that like natural geological features potentially such as dikes, you can find that they could be so variable compared to what the other material, and because obviously the completely different potential composition. Do you ever find that you could use those to in a way manipulate the blast force so it can act in a more softened, cushioned way? And then kind of as well, if you've got like faults depending on how they're sealed with the material, can you then, in a way, it's like how accurate can you be? Can you almost in a way gauge the sort of energy dispersion along that plane dependent on the material that's been filled the fault?
Yeah, and so obviously, if you're blasting in a very large scale, that would be like maybe 5 or 2% of the total volume of the blast. So it wouldn't have like a very big impact on your overall production blast. But in the case of like on the hull, it could probably result in like part of your catchment berm being lost if it's orientated in the wrong direction. So yeah, it's hard to always accommodate the geology when you do the blast designs. But I have seen scenarios where, you know, they've, like, say, for example, your foliated system is like running on a spacing of like 1 meter or 0.8 meters. You know, you could adjust your hole spacing of your blast hole, you know, your blast hole spacing, you know, to be optimal within that joint spacing. But it is very hard to get that right. You could probably do it on a small scale easier than on a large scale, if that makes sense. I don't know if I've answered your question or not.
Yeah. That was very good. Thank you.
Okay.
Eddie, do you want to go? Eddie?
Eddie.
I think you're muted if you're speaking.
Can you hear me now?
Yes.
Does the joint orientation drive how the quarry develops and where you need to start from, let's say, or does it even affect the shape of the quarry, as it were?
It can actually, if it's going to, you know, play a major role, then you would want to take it into account in your planning before you start your blasting. So when you basically are designing your initial pattern layout, you would, so we use what's called polygons to define those blasting blocks, and you would optimize the shape and orientation of those polygons across your whole pit floor or whatever, or quarry floor, in order, and you would optimize the sequence to accommodate the jointing in the best possible way. If you found that, if you saw or predicted that that was going to be like one of your major things that it's going to impact your design outputs, if it's not going to be like a major impact, then you might not worry about it. So it's just, yeah, you would look at it right at the outset and decide like what is going to impact my design the most, and then you would take what's going to impact it the most into consideration. Did I get the question answered there?
Assume yes. Does anybody else have any other questions?
Hello, can you hear me?
Yes, Radhi, go ahead.
Yeah, hi. Thank you very much for the presentation. It's really insightful and interesting. I just wanted to ask you, as a current professional with such a broad experience, when it comes to geology and engineering geology, what would be the biggest piece of advice you'd give an early career professional such as myself? I'm currently doing an industrial placement with Atkins and really trying to pick small bits of advices from professionals with such a large experience. So yeah.
So my best piece of advice is find a part of it that you're passionate about, and then know what you want to get and follow your passion. But yeah, in my first few years, I think I followed the generic geotechnical engineer development program. And it didn't take me too long to get through that. And then I had a choice to either specialize into something that I really liked, which was this subject, or to stay on that generic path and you know, do the you know, the job that everyone else does. And yeah, so deciding to specialize has its risks, but it also, if you're really passionate about it, you know, it's very rewarding in that way. So yeah, if you want any more detailed advice, you're welcome to drop me an email or anything, and I can share like more details with you.
Yeah, that's definitely very good to know, and something I would note down on my agenda. But yeah, thank you very much for that.
Yeah, it's hard in the first few years, but I think after like maybe 5 years, you sort of know what you like and what you don't like.
Yeah.
Don't be afraid to try anything that just to get the experience as well, because the more you try, then the more you understand.
Yeah, definitely. Totally agree with that. Yeah, thank you very much.
Great question, Radu. Does anybody else have any other questions before we come to a close? No? Okay, let's give Sandy a virtual round of applause. Thank you so much for presenting. It's been great. Thank you for dealing with the IT issues. For everybody else, our meeting this month has been cancelled due to a clash, but we'll provide updates for next month as it becomes clear. Have a lovely evening, everybody. Thanks for joining.
Thanks, Sandy.
Thank you for
Thanks,
having
Sandy.
me.
Thank you, everyone.
The waffle for so long.
Very much. Very good.
Thank you. Bye.
I hope it was interesting.
Thank you very much. Cheers.
Thank you. Bye-bye.
Thank you.
So, Sandy, I'm not sure if I'll have access to the recording. I'll double check in the morning because sometimes I get a little
Okay.
Teams prompt. If I don't, can I just drop you a message and then we can find a way to send it across, and I can add it onto the YouTube, if that's okay.
Okay, no, that would be great. I'm not sure either, so I think I'm going to rely on your feedback
Yeah.
to me if you have it or not. And then if not, I'll have to find how to download it as like a, I don't know, I assume you download it as a media file of some sorts.
Yeah, sometimes I just get a link on, Teams on the chat pane saying, oh, your download's ready, but I don't know how that works if I've not organized it. But we'll deal with that in the morning. That's a morning problem.
Okay, no problem.
Thank you so much for today.
Thank you.
Take care. Bye-bye.
Bye.